Hi guys, and congratulations, you made it to the end of the semester. You've worked hard. I'm very happy for you. So going into the final, I wanted to make sure I put together a little final exam review video for you. So we're going to talk about the 3 types of functions that we studied this semester: linear, exponential, and quadratic. We'll hit the main points and main features of each type of function, and we'll go through an example of each type. So buckle in. Let's get ready for our final. So the first type of function that we studied in this class was, of course, the linear functions. And we know that we can describe a line using this equation. So this is the general form of a linear function, right? Y equals mx plus b, or f of x equals mx plus b. M is a constant. It represents the slope or constant rate of change of our line. And to calculate m, we divide the change in output by the change in input. So it's basically y2 minus y1 over x2 minus x1, okay? B is also a constant. It represents the y-intercept or initial value. It can be written as an ordered pair as 0b. X represents our independent variable or input, of course, and y or f of x represents our dependent variable or output. So really, you guys, the important features of a linear function are the slope, right, the rate of change, and the y-intercept, the initial value. So we saw 3 different types of functions this semester, and they all sort of behaved in different ways. So let's talk about how linear functions behave, okay? So linear functions can either increase, decrease, or be constant. How do we know whether they're increasing, decreasing, or are constant? Well, that just depends on the slope. If the function is increasing, so for example, this line right here, right? As the input gets bigger, the output also gets bigger. So our line is increasing. That just means we have a positive slope. M is positive. Another way to say that is that M is greater than 0. All that means is that the slope is positive, okay? All right, well, lines can increase, but they can also decrease, and we see that right here. We have a decreasing line. So as the input is getting bigger, the output's actually getting smaller here. Well, how do we know if our function is decreasing? Well, it has a negative slope. M is negative. So M is less than 0, and that's just another way to say that the slope is negative, right? So linear functions can increase, they can decrease, they can also be constant. And in that case, the slope would be 0, all right? We have a slope of 0. And that would be, for example, the line y equals 4, okay? So let's look, 1, 2, 3, 4. It doesn't matter where we are in our input, our output is always 4, right? That's just a horizontal line, okay? So the slope is 0. So linear functions can increase, decrease, or be constant. And how do we know what they're doing? How do we know how they're behaving? We look at the slope, okay? If the slope is positive, they're increasing. If the slope is negative, they're decreasing. If the slope is 0, it's a constant, okay? Let's now look at an example of a linear function. So let me read this off to you and then we'll talk about it. A water tank already contains 56 gallons of water when Cooper begins to drain it. Water flows out of the tank at a rate of 8 gallons per minute. Now, you guys know I always tell you, take 60 seconds, make a little movie in your head about what's happening. Read this 3 times and just think about, before you even look at the questions, what is actually happening. So we have this water tank, right? And it already contains 56 gallons of water. Now, like, I don't know about you, but like alarm bells are going off in my head. I just got a starting value, an initial value there of 56 gallons of water, okay? When Cooper begins to drain it, draining means that my water is going to be going down. It's going to be going less and less. And we just talked about the behavior of linear functions. So as my input is going to be increasing, my output should be decreasing, which means I'll probably have a negative slope, right? Water flows out of the tank at a rate of 8 gallons per minute. So we're even given the rate with this. We're given the slope. We're given the rate of change here. So the first part of our question says, make a table of values and use it to write a linear function. Now, some of you could probably jump right into this and write a linear function. You might have thought all those same thoughts as me, okay? I know what my initial value is, right? I know my b. So if I'm thinking about a linear function, I know I want it in the form of y equals mx plus b, right? Where m is the slope B is the initial value, the y-intercept. Well, I know my initial value. It's 56 gallons of water, okay? So I already know what that is, and I know my rate of change. I know my M. Water flows out of the tank at a rate of 8 gallons per minute. Now remember, if you do right off the bat see this and understand it, you do have to say to yourself, okay, is this rate an increase or a decrease? And because the water's draining, it's a decrease. So we need to remember to make that negative. So we, in essence, could actually already write our linear function. So we know what our M is. Our slope is -8. Okay. We know our initial value. It's 56. All right. If we want to put in terms of our function, our output is how much water we have. So we would write G of, and this is, our input is time in minutes. So I'm just going to write G of t equals -8t plus 56. All right. So some of you might have seen that, known it, gotten it right off the bat. If you didn't, that's fine. And these directions tell us to write a table of values, so it's something we're going to have to do regardless of whether or not you saw that right off the bat. So let's do that. But at least we know now what we're working towards, right? So here's my table of values. Now, before you can sit and write this table of values, you have to think about what your input is, what your output is, assign them smart variables, right? Smart labels. And also, don't forget their units, okay? At this point in the semester, you should be able to do that pretty quickly and pretty easily. So I'm not going to go into a lot of depth about that. If it's something you are still struggling with, you should email me so that we can talk about it, okay? So my input here is time in minutes, right? We know that this water tank is draining at a rate of 8 gallons per minute, okay? So I called my input variable t for time, and my units are, of course, minutes, all right? So that's where this whole left side of the table is coming from. And of course, my output is how many gallons do I have, my total gallons, okay? This question is given to me in gallons of water. So I gave that the smart label G of t. G, of course, stands for gallons, and we know that this depends on our time, our input, okay? Our function is always dependent on our input. And that is just representing the total gallons of water in my tank. So obviously my units are gallons, okay? So I know that when 0 minutes have gone by, before it starts draining, I have how many gallons, you guys? 56. And how I got the next value was, well, after a minute, I know that the water is flowing out at a rate of 8 gallons per minute. So when 1 minute has gone by, I'm going to lose 8 gallons. So I just did 56 minus 8. Okay. Then another minute's going to go by. So after 2 minutes, now I'm losing another 8 gallons. So I subtracted 8. Okay, that gave me 40. And after 3 minutes, now I've lost another 8 gallons. So 40 minus 8 is 32. That's where this came from. And then another minute goes by, and of course I lose another 8 gallons. So 32 minus 8 is 24. All right. Now, we know we need to get our function in the form of y equals mx plus b. And of course, we immediately saw that we were doing what? I shouldn't have erased that. Minus 8, minus 8, minus 8. So we are taking away 8 as our input changed by 1. Okay? So we're just jumping 1 on the input. And our inputs should always be increasing, you guys, all right? Our inputs will always be increasing. Our outputs are a different story. So if we're thinking about change in y over change in x, we're losing 8 as we go up by 1. So what's our slope? -8, right? Which we knew, but if we didn't, we could easily figure it out from this table. And we also see that our initial value is right here when we have 0. When 0 minutes have gone by, how many gallons of water do we have? 56. So we have our m, it's -8. We have our B. It's 56, okay? So now we can just plug that right in. And I'm going to sort of just make some space because I know what I put on the slide already. So there's our function. G of t equals -8 plus 56, right? Okay, our m is right here. Excuse me, our b is right here. Our m is right here. And I just plugged in my smart variable, my variables that I gave smart labels to, instead of y and x, okay? Because we're writing this function in terms of this particular problem. All right, and you could also write it. I know some of you like to write the initial value first when you have a negative slope. That's fine. These are exactly the same. These two functions, linear functions, are exactly the same. Okay, g of t equals -8t plus 56 is the same as g of t equals 56 minus 8t. For some people, I know this is much more intuitive because you're saying, okay, I'm starting with 56 gallons and I'm taking away 8 gallons every minute. All right, so if that's more intuitive for you, that's fine. They're exactly the same function, okay? So that is the first part of our example for linear functions. Okay, guys, so now we're going to look at a few more questions to go along with this example, okay? And these are the same kinds of questions we saw when we did this, our chapter on linear functions. So this is the same problem from the previous slide, and we already were able to write a function for it. So we said g of t equals 56. We start with 56 gallons, and we're losing 8 gallons every minute, okay? So g of t equals 56 minus 8t. Now for linear functions, and even for exponential and quadratic, when you're being asked questions, usually you're either going to be given g of t and solving for t, or given t and solving for g of t, okay? You're either going to be given the output and solving for the input, or vice versa, you're going to be given the input and solving for the output. So it's really just your job to determine what you're given and what you're solving for, okay? You're going to be given one variable and solving for the other. So let's look at letter B. How much water will be left in the tank after 6 minutes? So you stop and say to yourself, oh, okay, am I being given the input or the output? And in this case, you're being given the input, okay? You're given t. 6 minutes, that's the time. I need to know how much water will be left in the tank, how many gallons. So I'm given t and I'm solving for g of t, okay? All right, so let's do that. G of t equals what when t equals 6 minutes? So all we're going to do is we're going to take our original function, g of t equals 56 minus 8t, and we're going to plug in 6 for t. Okay, always start with your original function, g of t equals 56 minus 8t. We're plugging in 6 for t, so g of 6 equals 56 minus 8 times 6. All I did was replace that t with a 6. 8 times 6 is 48, and 56 minus 48 is 8 gallons. So that means when the tank has been draining for 6 minutes, we're going to have 8 gallons of water left. And actually, we can even deduce that it's going to take 7 minutes to fully drain this tank, because if it took 6 minutes to get us down to 8 gallons, we know that after another minute, we're going to lose another 8 gallons, which will leave us with nothing. It's just a little nugget we can put in the back of our head for now. All right, so in that, for question B, we were given the time and we needed to solve. So we were given the input and we needed to solve for how many gallons, the output. All right. Let's look at letter C. How much time has gone by if there are 27 gallons in the tank? So now we're sort of doing the opposite. We're given the output, we're given g of t, and we're being asked to find the time. We're being asked to find t. So we're going to plug in 27 for g of t, and we're going to solve for t. All right? So t equals what when g of t equals 27 gallons? So I just plugged in 27 for g of t, which gives me 27 equals 56 minus 8t. I can now solve for t. I'm going to subtract 56 from both sides. That gives me negative 29 equals negative 8t. And then, of course, I divide by 8 to give me t equals 3.625 minutes. Okay, remember our time is in minutes. You always want to make sure you have the right units, the proper units. All right. So in that case, for this second part, or third part, I should say, letter C, we were given the output and we solved for the input. For letter B, we were given the input and we solved for the output. So you're either going to be given the input and solving for the output, or given the output and solving for the input. Letter D, how long will it take for the tank to fully drain? Now, this is the same concept, guys. You're given one variable and you're solving for the other. It's just not as obvious. This one's going to require a little bit of thought because we don't see any numbers here, so we have to sort of interpret this question. So it's asking, how long will it take for the tank to fully drain? How long? That's a time. So we're looking for t. We're looking for a time. Will it take for the tank to fully drain? And that's really the piece you need to interpret. If the tank is fully drained, what's our output, guys? How many gallons of water do we have? 0. So we are given the output. It's 0. And we're going to solve for the input. It's just not as super obvious as it was in the other problems because you don't see any numbers floating around here. But you're intelligent. You can just stop and think for a second and figure this out, right? So we want to know what's t when G of t equals 0 gallons. We have the tank is fully drained. What does that mean? It means there's no water left. There are 0 gallons of water. So we're just going to plug in 0 for G of t, which gives us 0 equals 56 minus 8t. And now we're going to solve for t. We bring the 56 over by subtracting it. That gives us negative 56 equals negative 8t. When we divide negative 56 by negative 8, we get t equals 7 minutes. And we sort of already knew that, right? We figured that out up here in letter B when we were like, oh, after 6 minutes, we're down to 8 gallons, which means it's just going to take 1 more minute for it to fully drain. And we were right. Okay, so it's going to take 7 minutes for this tank to drain. Now, you might have realized that you might not have, but that's actually the x-intercept, right? So we always write ordered pairs, input, output, right? Let's write the ordered pair for what we just saw for in letter D. The input here, our input is t, is 7, and the output is g of t, which is 0. Okay, if we graph that, 1, 2, 3, 4, 5, 6, 7. Okay, that brings us here. Okay, so this is our time, how much time has passed, and then these are how many gallons of water we have. So that is indeed our x-intercept. We just found our x-intercept here, okay? And if I'm just going to move this because I want to extend this axis up. And if we think about this problem, right, we know that we started with 56 gallons of water, which should be probably even higher than that, but I'm just going to say way up here. So we started when 0 minutes had gone by, we started with 56 gallons of water, and then we lost water until the tank was fully drained. So this is sort of our little graph here, and it makes sense that we would have this negative sloping line, right? Because we have a negative slope, so our line should be decreasing like that. So I put this here for a reason. You'll see why I put it here in the next problem. It says, letter E says, what is the real world domain and range? And this is something we've struggled with throughout the semester, so I thought it was something that we should really hit on. So real world, first of all, it says real world domain and range, which means I only am concerned with the domain and range for this problem. Only the numbers that make sense in context of this problem, right? This line, g of t equals 56 minus 8t, it could extend. It does, in fact, extend beyond this, right? It would just keep going up and down, but we're not concerned about those other values. We're only concerned about the values on this line right here, okay? That's all we're concerned about. So domain are all the possible inputs we could have, and range are all the possible outputs that we can have in this problem. And if it's something you struggle with, I highly recommend drawing out the graph, graphing your line, because it makes it very, very clear, in my opinion, what your domain is. And what your range is. So we said that domain, right, represents all the possible inputs. Well, our input for this particular problem is time, which means all of our possible inputs are along the x-axis. So this problem about this draining water, right? It's going to start with 0 minutes having gone by, right? At 0 minutes, we have this 56 gallons of water. And then the water is going to drain and drain and drain and drain and drain and drain until we get to 7 minutes. And then there's nothing left to drain, right? Our tank is fully drained. So our tank was draining from 0 minutes up to 7 minutes, okay? So the possible inputs, the domain, our time, t, can go from 0 to 7. So our domain is from 0 to 7, and you always want to use the label, the units, minutes, okay? And if you didn't know that, that's why I say drawing the graph is really helpful, because you can clearly see that your inputs go from 0 to 7 and then stop, all right? What about the range? The range is all your possible outputs, and in this problem, that was how many gallons of water did we have. So we started with 56 gallons of water, and then it drained and 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 drained until we had no water left. All right, so our range, our outputs, our G of T, go from 0 to 56 gallons, right? We had anywhere from 0 to 56 gallons of water, all right? So if you draw the graph, you guys, it makes it a little bit more visual and clear, your ranges of values there for your domain and your range. So if it's something you struggle with, I recommend drawing the graph. Okay, so now let's move on. And I did want to just take a second, I know we sort of already talked about it, but just devote a slide to the graph of the function, right? The graph tells us so much information. I mean, we see all the important things we talked about for this particular function, g of t equals 56 minus 8t. We can clearly see that this line is decreasing, which means we have a negative slope, right? And that makes sense because the water is draining. Our output should be decreasing as time goes on. And we can see it takes 7 minutes for it to fully drain. That was our x-intercept. And of course, our y-intercept was our starting value, which is up here at 56. Okay? So the graph tells a great story, and it is important to be able to sort of pick out these important features of the graphs of these types of functions we talk about, right? The x-intercept, very important, tells us how long it took for our tank to drain. The y-intercept, very important, it tells us how many gallons of water we started with, all right? And where do those fall on the graph? Well, that's where they fall, right? That's what this is supposed to look like. And we can clearly see that negative slope, that decreasing line. Okay. So now that we've talked about linear functions, let's jump to chapter 3 and talk a little bit about exponential functions. What are they? Well, an exponential function is defined by an equation of this general form, or f of x equals a times b to the x, where a cannot equal 0 and b cannot equal 1 and has to be greater than 0. So what does all this gobbledygook mean, right? So x is, of course, the independent variable, the input. And we saw when we were working in this chapter on exponential functions that our input, our independent variable, was almost always time, some measure of time going by. So you can almost always rest assured that when you're dealing with exponential functions, whatever value of time you're dealing with is going to be your input, your exponent there. So hopefully that can make it a little bit easier if you're somebody who struggles with figuring out what's my independent variable, what's my dependent variable. Well, your independent variable is going to be whatever that measure of time is. And then your dependent variable will be whatever else the problem is asking you about. Okay? Y is the dependent variable, the output. A is our constant called the initial value. So when we were talking about linear functions, we had y equals mx plus b, and our initial value was b. Well, for exponential functions, our initial value, our y-intercept, is going to just be a now. We just call it something different. But it's the same concept. It's your initial value, however much you're starting with. And now instead of calling b the initial value, we're calling it the constant multiplier, okay? So in linear functions, we called that rate of change m. Well, for exponential functions, we're just calling it b. We're giving it a different name, right? Why can't a be 0, you guys? A cannot be 0 because, look, if a were 0, it would make all of this go away. It would be 0 times b to the x, which would just be 0. So you would just be dealing with the line y equals 0, which is what? Your x-axis. So that doesn't make any sense. A can't be 0. Otherwise, it's not an exponential function anymore. It's a line. Okay, why can't b be 1? Why can't your constant multiplier be 1 right here? Right? It says b cannot equal 1. Well, think about it. 1 raised to any power. So if b is 1, if you raise that to literally any power, it's going to be 1, which means this function becomes a times 1. A is just a constant. So you're back to a line. All right? So if b equaled 1, you no longer have an exponential function. You have a linear function again. So b can't be 1. And b has to be positive because we don't want to be raising a negative base to a power. That's going to give us some really messy stuff. So b has to be positive. Okay? And we call it the constant multiplier. And we called it a few different names, as a matter of fact. We called it the constant multiplier. We called it the growth factor, the decay factor, the multiplier. There's a lot of different names for b. But for our purposes right now, we're going to call it the constant multiplier. Exponential functions have inputs that increase by a constant while the output's changed by a constant multiplier. So this was a little different, right? If we think about it in terms of tables of values, when we were looking at linear functions, as the input was increasing by a constant, we saw that the output was either increasing or decreasing. We were either adding or subtracting the same thing along the output. Here, we're going to be multiplying along the output, okay, by some constant. It's a little bit different. So we talked about how linear functions behave. Let's talk about how exponential functions behave, all right? And we talk about exponential functions, the behavior of exponential functions in terms of exponential growth and decay, okay? Exponential functions can either increase or decrease, and it happens very quickly, okay? If you're talking about exponential growth or decay, it's going to happen very quickly and dramatically, which is a little bit different than linear functions. So here we have two different exponential functions, one modeling exponential decay, which you can see in red, okay, right here, and one modeling exponential growth, which you can see in blue, okay? And you can see the exponential decay in red, you can see how that's decreasing as time goes on, right? And then, of course, the exponential growth, you can see it starts small and then it increases, okay? That's why it's growth. So for linear functions, we saw that when our line was either increasing or decreasing or constant, it was very dependent on the slope, right? If our slope was positive, our line was increasing. If our slope was negative, our line was decreasing. So let's see what this means for exponential functions. So if an exponential function is increasing, we say that they have a growth factor of b, where b is greater than 1, okay? So let's look at this right here. We're looking at exponential growth, right? Well, here's our growth factor, b, okay? And it is indeed greater than 1, right? Then it's 2. 2 is greater than 1. That just means this function is doubling as time goes on, right? From one output to the next, we're doubling and doubling and doubling and doubling. So yeah, of course, we're getting bigger and bigger and bigger. That should sort of make sense, right? If our constant multiplier is greater than 1, then our function will indeed increase, okay? So we no longer call b our constant multiplier, we call it a growth factor because our function is growing, it's getting bigger. So again, just like with linear functions, whether or not our function was increasing or decreasing was dependent on the slope. Here again, it's dependent on the constant multiplier. All right, so those rates of change are very, very, very important. They really determine how our functions behave. If our exponential function is decreasing, then we say they have a decay factor of b. So now we're no longer dealing with growth, we're dealing with decay. So where b is between 0 and 1, meaning that the constant multiplier is between 0 and 1. So if we look at our function in red over here on this graph, right? Our b is 1/2. 1/2 is between 0 and 1. So we are dealing with decay, and you can clearly see that that exponential function is decreasing, right? It starts out big up here, and then it just gets smaller and smaller and smaller very quickly. And it will actually, that was very deceiving. It will never hit that x-intercept, right? That's an asymptote. So that should make sense to you guys if you stop and think about this for a second, okay? This means that as time is going on, we're having our output, excuse me. So as time goes on, it's being chopped in half. So if we're starting with, we did a lot of problems about cells, right? So if we're starting with 1,000 cells, well, the next day there's going to be half that many. So we're chopping them in half, okay? And then the day after that, so if we're starting with 1,000, we're going to have 500 the next day, right? And then the day after that, we're chopping those 500 cells in half. We're going to have half that many, so we're going to have 250, right? So it should sort of make sense why our function is decreasing, okay, when we're dealing with a fraction, a number between 0 and 1, when our constant multiplier, our decay factor, is between 0 and 1. Because if we are between 0 and 1, we're dealing with some decimal, some fraction, which means we're chopping however much we had into smaller and smaller bits, okay? So we can either have exponential growth, in which case our b, our constant multiplier, is a growth factor, and it is greater than 1, or our exponential function can be decreasing, in which case our b, our constant multiplier, is a decay factor, and it's between 0 and 1. I don't want you to get confused and think that our b is decaying. For us to have decay, our b has to be negative. No, 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 no. That's only with linear functions when we're talking about negative slopes. Remember, we can't have a negative b at all, ever, for exponential functions. So if we're dealing with decay, we're dealing with a fraction, okay? We're dealing with a fraction or a decimal, a number between 0 and 1, okay? So when we're talking about the behavior of exponential functions, we really do need to also talk about asymptotes. This was a new concept. And it's important when you're talking about exponential functions. So an exponential function of the form f of x equals a times b to the x will get closer and closer and closer to the x-axis, but will never actually touch it, okay? Our function, our exponential function, is never, ever, ever actually going to get to touch that x-axis, which means we will not have an x-intercept. Okay, there are no x-intercepts for exponential functions. Very different than a linear function. This means that the x-axis is an asymptote. All an asymptote is, I should say, is a line that your function will never touch. Okay? So the x-axis is an asymptote. Our exponential function will never touch it. Okay? And you can see there's 3 different examples here. All right? We have 2 of them. We have y equals 2 to the x, y equals negative 0.1 times 2 to the x, and y equals negative quantity 2 to the x, okay? And in every single one, they're all approaching the x-axis, but they're never, ever actually touching it, okay? So that's important. They'll never actually get there. They'll get closer and closer and closer and closer to it forever, but never touch it, which is kind of crazy if you stop and think about that. All right, now let's look at an example of exponential functions. So a doctor administers 500 milligrams of medicine to a patient. The level of the drug in the bloodstream decreases by 6% every hour. And like I always say, take 60 seconds, make a picture in your head, and really think about what's happening. Think about what your input is, what your output is, what your independent variable is, what your dependent variable is. So we have a doctor, okay? He has this patient who's sick, and he needs to give this patient 500 milligrams of medicine. The amount of medicine in that patient's bloodstream is going to decrease by 6% every hour, all right? So every hour that passes by, they have 6% less of that 500 milligrams of medicine in their bloodstream. Okay, so that's what's happening. The first part of this question says, write an equation for this function. Before you can do that, guys, you need to think about what's my independent variable and what's my dependent variable. And do you remember 2 slides ago, I said for exponential functions, we noticed that our input was our independent variable was pretty much always time. And it's the same for this one. And that's a pretty good rule of thumb for the questions you're going to be asked. You've been asked about exponential functions, right, that you saw in this chapter. So you can pretty much assume that your input, your independent variable, is how much time has gone by since this patient has been administered this medicine, okay? So our independent variable, our input, we're going to call time. This is given to us in hours, okay? And I gave this the smart label T, and of course my units are hours, all right? Because that's what we were given in the problem. Which means my dependent variable is the amount of medicine in the bloodstream for our patient. Okay, the units we were given are milligrams, and I'm just going to give this the smart label M of T for medicine over time. Okay. Now, we know that we need to write an equation for this function in the form f of x equals a times b to the x, where a is, of course, our initial value, and b is our constant multiplier, which will either be a growth factor or a decay factor. Right off the bat, we can say to ourselves, oh, b is going to be a decay factor because, look, it's decreasing. We know the amount of medication is going down, okay? So we are decreasing by 6% every hour, all right? And we know our initial value, guys, okay? How much medicine did we start with? 500 milligrams. So we know our A already. We know a lot already. So our A, our initial value, equals 500 milligrams. Okay, we know that the amount of medicine in the bloodstream is decreasing by 6% every hour. Okay, I need to convert that 6% to a decimal, which gives me 0.06. That's my decay rate. So how do I find my decay factor, you guys? I do 1 minus my decay rate, all right? So my decay factor B is going to equal 1 minus my decay rate, which we called R, okay? Right, we call that R up here. We know R is equal to 0.06, so I'm just going to plug that right in. So 1 minus 0.06 is 0.94. So there's our decay rate, and that should make sense because remember, when we're dealing with exponential decay, what did we say? Our decay factor. Our decay factor had to be between 0 and 1. 0.94 is between 0 and 1. It's less than 1 and greater than 0. Okay, so that should make sense already. We should be thinking, okay, good, we're on the right track. So now we have our initial value, we have our A, and of course we have our decay factor B. So now it's going to be really easy to write this function. That leaves us with the function M of T. Remember, we labeled our output M of T equals 500, our initial value, times, and what was our B, our decay factor? 0.94. So we just plug that in. And then, of course, we're not going to say X because we labeled our input T. So that leaves us with T up here. So our function is M of T equals 500 times 0.94 to the T power. There's our function. We start with 500 milligrams of medicine, and every hour we're losing 6%, okay? So now let's look at a few other questions, okay? Letter B says, how much medicine will be in the patient's bloodstream after 4 hours? So just like when we were solving for our linear functions, we were solving questions, answering questions concerning our linear function in the first example. We are also going to sort of have the same line of reasoning for this example. We're either going to be given the input and solving for the output, or given the output and solving for the input, okay? So remember, our function, let me write it at the top, is, oops, not G. I'm back in the last example. So the amount of medication, M of T, over time is going to be equal to 500 times 0.94 to the T power. That was the function we just generated on the last slide, okay? So now we're either going to be given t and solving for m of t, or given m of t and solving for t. Let's look at letter B. How much medicine will be in the patient's bloodstream after 4 hours? 4 hours is a time. So we're given the time, which means we're going to need to be solving for the how much medicine, okay? So m of t equals what when t equals 4? Well, let's plug 4 in for t. M of t equals 500 times 0.94 to the t power. Always start with your original function, plug in what you know. So m of 4 equals 500 times 0.94 to the 4th power, which gives us approximately 500 times 0.78, and that is 390.37 milligrams. And guys, I'll always tell you how to round. So on the final, if rounding is required, I'll tell you what decimal place to round to, okay? So after 4 hours, that patient will have approximately 390.37 milligrams of medication in their blood, okay? Let's look at letter C. If the patient needs at least 150 milligrams in her bloodstream, after how many hours should she get another dose? So guys, again, this is the same kind of problem we've been dealing with. It's just a little bit disguised. I don't want these words at least to throw you off, to think that you have to be dealing with some sort of inequality. No. Okay, that just means that we need to figure out how long it's going to take for the amount of blood, or excuse me, the amount of medication in her blood to get down to 150. So we're basically given m of t, 150, right? We want to solve for how many hours is it going to take for her to have 150 milligrams of this medication in her bloodstream. So we're given m of t, and that means we need to solve for t, right? We're given the output, and now we need to solve for the input. Just need to take a minute and just really think about these problems. And if you do that, you'll be fine. So t equals what when m of t equals 150 milligrams, okay? So we're just plugging in 150 for m of t. So that gives us 150 equals 500 times 0.94 to the t, which gives us 0.3 equals 0.94 to the t. What do we need to use logarithms to solve for t now? Okay, they're sort of the inverse operation here. So that gives us t equals log of 0.3 divided by log of 0.94, which is this approximately 19.46 hours. Okay, so in approximately 19.5 hours, approximately 19.5 hours, she'll be down to 150 milligrams of this medication in her blood, and she has to have at least that much. So the doctor's going to need to come in and give her another dose. All right. And then, of course, letter D, if the patient needs at least 150 milligrams in her bloodstream, what is the real-world domain and range of this function? Okay, I really want you guys to feel comfortable with domain and range going into the final. So that's why we're going to keep going through domain and range for each of these examples. So remember, domain is input and range is output. All right. For domain, when we're talking about inputs, our input here is time. Okay, so how long, how many hours is this going to go on? So again, we know that the patient needs at least 150 milligrams in her bloodstream. So how much time is going to go on from when she's got 500 milligrams in her bloodstream to 150? We just figured that out. All right, our domain, our input, is going to go from 0 hours to 19.46 hours because we know at 19.46 hours, she's going to have 150 milligrams of this medicine in her bloodstream. And after that, she's going to need another dose, okay? So the clock's going to restart. Our input's going to restart. So the amount of time that can possibly go on for this function, for our purposes anyway, for this particular, whatever this medicine is 0 to 19.46 hours, okay? After that, she's going to have to get another dose, which means it's just going to start over, okay? I'm going to go back to 0. And what's our range? Well, she has to have at least, remember, range is our output, how much medicine she has in her bloodstream, right, our M of T. Really always think about what your input and output are representing. That's going to help you figure out domain and range. So we need to know how much medicine can she possibly have in her bloodstream. Well, we know she has to have at least 150 milligrams, so that's going to be the low end, okay? And the doctor is going to administer no more than 500 milligrams. So at any given point, she'll have somewhere between 150 to 500 milligrams. All right, and always make sure you include your units. Okay? So now let's move into and look at the graph for this function. Okay, so let's look at the graph of this function. All right, this is the same situation we've been dealing with. A doctor administering 500 milligrams of medicine. The level of the drug in the bloodstream decreases by 6% every hour. So we have our function m of t equals 500 times 0.94 to the t, okay? And you can see that, as we've discussed, this is decay, right? You can clearly see that this function is decaying just by looking at it visually, right? It's going down. And like I said, it will get really, really close to the x-axis, but it will never actually cross it. Okay, and we know that we're only concerned about this function from an input of, it's about 19.5 hours, right? So from 0 to like here. When we have, because she has to have at least 150 milligrams of medicine in her bloodstream. So we're sort of only concerned about this one small piece of our graph. So this is what we're concerned about. 500 milligrams in her bloodstream to 150. So this is like our chunk of the graph. Okay, but I wanted you to be able to see that exponential curve, you know, that we know. Exponential functions look like that, right? Or if they're increasing, of course, they look like this. So I wanted you to be able to see that curve. If we had extended this graph out, it does make that nice little curve as time continues to go on, right? This is going to continue on with that exponential curve. That will get really, really close to the x-axis, but will never actually hit it. Okay? All right, so let's move into our last chapter, chapter 4 on quadratic functions. What are they? A quadratic function can be defined by an equation of the form y or f of x equals ax squared plus bx plus c, where a cannot equal 0. And why can't a equal 0, you guys? Because if a equals 0, this would go away, and we're just left with a line, okay? And it would no longer be a quadratic function. So x is the independent variable, the input. Nothing unusual there. Y is the dependent variable, the output. And a, b, and c are constants, okay? And we really talked a lot about how when we're dealing with quadratic functions, this whole idea of the second order is really important. So ax squared plus bx plus c is a second order polynomial, which just means that the highest exponent we're dealing with is 2. The highest power is 2. We call this the degree. The highest degree is 2. All right. Quadratic function tables are tables of values characterized by constant second order differences of the output when the input increases by a constant. So again, this whole idea of this second order, it's a second order polynomial, and when we're looking at a table of values, it's the second order differences that are constant, okay? So when we look at the first order differences, they're going to be all over the place. But when we then figure out the differences between those will be constant as our input is increasing by a constant. Graphs of quadratics are parabolas, those fun little U shapes that will either be concave up, pointing up like a smile, or concave down, pointing down like a frown, okay? Those parabolas. And parabolas, we learned, are very useful in the real world. So quadratic functions are incredibly useful in real life. So just like we talked about how linear and exponential functions behave, let's talk about how quadratic functions behave. So a parabola is either concave up like a smile or concave down like a frown. It's just concavity just means how is the curve bending, okay? So if we're given the quadratic function f of x equals ax squared plus bx plus c, if a, this first coefficient in front of your x squared term, okay, if a is positive, okay, if a is greater than 0, which is a fancy math way to say if a is positive, the parabola is concave up. Okay, so here we have the graph of the function y equals x squared minus 10x plus 19. Our a is, of course, positive 1, okay, which is positive, which means our parabola is concave up like a smile. Yay! If a is negative, if a is less than 0, which is the fancy way to say negative, then the parabola is concave down. All right, so here we have the function y equals negative x squared plus 10x minus 19. And of course, our a is negative 1. So our parabola is concave down like a frown. Right? So just like when we were talking about linear functions, right, lines, if our slope was positive, then our line was increasing. And if our slope was negative, our line was decreasing. Well, for quadratic functions, if that a coefficient is positive, your parabola is concave up. And if that a coefficient is negative, your parabola is concave down. Okay? We also need to talk about the vertex and the axis of symmetry when we're talking about how do quadratic functions behave. So let's take a minute to talk about those. So the maximum or minimum point on the ordered pair xy is known as the vertex, okay? The x coordinate of the vertex, which we just sort of denote as x sub v, is negative. We calculate that by using the formula negative b over 2a. And the y-coordinate of the vertex, how do we figure that out? Y sub v? Well, we just take whatever we get for x and plug it in to the function. So it's f of negative b over 2a, okay? So we're basically just finding out whatever the x value is here, and then we're taking that and plugging it into the function to solve for the y value. All right, that's all that means. So the vertex, okay, is either going to be a maximum or a minimum, as I said. And how do you know which it's going to be? Well, if your graph is concave up, like it is here, then it's going to be a minimum. Okay, the vertex is just the point at which your parabola changes direction. So here it's going down, 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 and down, and then we hit this point, right? And it starts to go up, 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 right? So when we have a parabola that's concave up, we're going to be dealing with a minimum point because our graph changes direction down here at the bottommost point in our graph. If we were dealing with a parabola that was concave down, like this, okay, then we'd be dealing with a maximum point, okay, at the top. And visually, that should make a lot of sense, right? Like, obviously, this point is a minimum because it's all the way at the bottom. All right, and vice versa, this point would be a maximum. So whether or not you're dealing with a maximum or minimum really depends on concavity, which depends on if your a is positive or negative, okay? And you can figure out this point by using this lovely formula, okay? So the minimum here, our vertex, is 5, negative 6, okay? The axis of symmetry is the vertical line that goes through the vertex, or the line x equals negative b over 2a. So it's just this line that cuts our parabola in half, okay? That's what the axis of symmetry is. It is always going to occur, that line is always going to go through the vertex because the vertex is sort of like that centermost point of our parabola. So if we want to cut it in half, yeah, of course our line has to go through it. So if you know the vertex, you also know the axis of symmetry, okay? Whatever x value you get for your vertex, well, your axis of symmetry is just that line. So here we got 5 for the x value of our vertex, right? So then our axis of symmetry is x equals 5. It's the line going through that point, okay? And then, of course, we know that intercepts are incredibly important. So we also need to just take a minute and talk about intercepts in terms of quadratic functions. So the y-intercept of any parabola is the point 0, c. Okay, so whatever your c constant, your c coefficient is, your c constant, that is the y value of your y-intercept for your parabola, okay? So here, if we look at this function right here, well, our intercept, our y-intercept, is just going to be 0, 19. Okay, 0, c. Our c is 19. So that means our y value, our y-intercept, is going to be the point 0, 19. And that should make sense because we know when we're calculating intercepts, right, you guys, we just plug in 0 for the opposite variable. So if we want to find the y-intercept, we plug in 0 for x, and if we plug in 0 for x, these two terms are going to go away, and we're just left with c. Okay, so we plugged in 0 for x, and we got c. So that's where that comes from. X-intercepts are a different story. So to find the x-intercepts of a quadratic function, we use the quadratic formula, which says x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. That will give you your x value, and your y value is, of course, 0, okay, for your ordered pairs. Because, again, we're looking for the x-intercepts, so we plug in 0 for y, right? So you will either have 0, 1, or 2 real x-intercepts, okay? And they will be of the form x, 0, okay? So whatever you solve for and get for x, you plug in for your x coordinate, and of course your y coordinate is just 0, because we're dealing with the x-intercept here. So now let's look at an example for a quadratic function. And we talked a lot about how quadratic functions model projectile motion really well. So this is a projectile motion problem. The function h of t gives the height of a rock thrown off the Golden Gate Bridge in feet above the water t seconds after it is thrown. And here it is, h of t, the height, equals negative 16t squared plus 30t plus 225. So always, 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 I'm going to say it to you every single time, take 60 seconds and just before you look at any of the questions, stop and think about what is happening in this problem, you guys, okay? So somebody is standing on the Golden Gate Bridge and they take a rock and they throw it off, and it's going to go through the air until it eventually hits the water, right? First it's going to sort of go up, and then it's going to go down, down, down into the water, right? And we can model that with this quadratic function, okay? So the height that the rock is above the water depends on how much time has gone by. All right. Whenever you do these problems, you guys, again, take a minute and visualize it, and then write your A, B, and C, okay, before you answer any of the questions, because you are going to use them probably for every single question that you answer. So always just take a minute and write your coefficients. So in this problem, our coefficient A is, of course, negative 16. Okay, our coefficient B, that always comes before our x to the first power, so is 30. And then, of course, our coefficient C is 225. Okay, always write those out first. It will make your life so much easier. Okay, and just like write them really big at the top of your paper, highlight them, box them, whatever, so you don't lose track of them. You can constantly refer back to them. Make sure you always take negative signs with you. That's super important, and that's where a lot of people tend to make mistakes. If your coefficient is negative, you guys, you have to take that negative sign with you. So we had a negative 16t squared, so our A is negative 16. If this had said minus 30t, then our B would have been negative 30, okay? So you always want to make sure you take those negative signs with you. What is the rock's maximum height? That word maximum should jump right out at you. We just talked about how parabolas either have a maximum or a minimum, right? That's the vertex, and that's the point where our parabola changes direction. And we know that this parabola is going to be concave down because our A is negative, right? Our A is negative 16. So that means that this parabola is going to be concave down. Okay, which, yes, means we have a maximum, right, at topmost point. Where does that maximum occur? It occurs at the vertex, right? The maximum is the vertex, and we have a formula for the vertex. We know that the x-coordinate of the vertex is equal to negative b over 2a, okay? We know that. We just talked about it. So all I need to do is plug in my b and my a. My b is 30. Okay, so notice I took this negative sign, negative b, or b is 30, all over 2 times a. My a is negative 16, of course, so I just plugged in negative 16. And if you solve that out, it gives you 0.9375. That is not the answer, you guys. That is the x coordinate. That is our input. Height is our output. That's really important to realize, which is going to be our y coordinate. So we need to take this x value and plug it into our function. Okay? We need to find the y value, the value for that. What is my output after 0.9375 seconds have gone by? What's the height? That's what I have to solve for. Okay? We want to know the rock's maximum height. So I need to be solving for the output here. So I've got that the maximum height occurs after 0.9375 seconds. So now I need to take that and plug it into my function. Everywhere I see a t, I need to plug in 0.9375. Remember, your x, your input, is your t. Time is your input here. So let me do that. So now everywhere I see a t in this function, I'm just plugging in 0.9375. Okay, so I have negative 16 times 0.375 squared. All right, always make sure you put that value, whatever that value is, in parentheses so that you wind up taking whatever sign it has with you. Plus 30, okay, plus 30 times t, and again, t is 0.9375. Plus 225. So I just took my function, you guys, and I plugged in t equals 0.9375 everywhere I saw a t. Okay, and if I solve that out, so first I'd square 0.9375, multiply it by negative 16. Then I'd add 30 times 0.9375 to that, and then add 225 to that, and that gives me approximately 239 feet. That is the answer. Remember, this asked you for the height, the maximum height. Height is your output. So once you've found the input, you need to plug that into your function to get your output. So it's approximately 239 feet. So that is how high above the water. Always go back and try and interpret your answers in terms of the problem. That means the rock will get to a maximum height of 239 feet above the water before it starts to fall down towards the water. Okay, that's all. That's what's happening there. Okay, so now let's look at some more questions concerning this problem about our rock. So letter B says, how long until the rock is 89 feet above the water? So just like with our examples that we looked at with our linear functions and our exponential functions, we're either going to be given the input and looking for the output, or we're going to be given the output and looking for the input. So for this particular problem, our input is how much time has gone by, so t, and our output is the height above the water that this rock is, so h of t. So if we look at this question, it says how long until the rock is 89 feet above the water? 89 feet is a height. So we're given the output, which means we're looking for the input, okay? So if h of t equals 89 feet, how much time has gone by? How long did it take the rock to get to 89 feet above the water, all right? And remember, we're starting at 225 feet, so the rock has definitely been in the air for at least some amount of time if it's gotten down to 89 feet above the water. So all we're going to do is plug in 89 feet for h of t, all right? And then solve for t. So let's do that. Okay, always start with your original function, h of t equals negative 16t squared plus 30t plus 225, and then plug in from there. We know h of t is 89, so that gives us 89 equals negative 16t squared plus 30t plus 225. Let's move that 89 over, so subtract 89 from both sides. And that gives us 0 equals negative 16t squared plus 30t plus 136. Once we have our quadratic function set equal to 0, we can go ahead and use the quadratic formula to solve, okay? In this case for t, right? Usually we'd say for x, but here our input isn't x, our input is t, right? We named it t for time. So we now have, it's important for you guys to take notice that we now have a new c. Our a stayed the same, it's negative 16. Our b stayed the same, it's still 30. but now our c changed to 136. That's important to notice because, of course, when you use the quadratic formula, you need to have a value for a, b, and c. So now we're going to take those values. So we have a equals negative 16, we have b equals positive 30, and we have c equals 136, and we're going to plug those values into the quadratic formula, okay, to solve for t. So t equals negative b plus or minus the square root of b squared minus 4ac over 2a. So if we plug in our a's, our b's, and our c's, that gives us t equals negative 30 plus or minus 30 squared minus 4 times negative 16 times 136 all over 2 times negative 16. Always, always, always deal with what's under the square root first. So when you start with this problem, you're going to be dealing with this stuff underneath the square root, okay, this stuff right here. So you're going to start with the 30 squared, okay, minus 4 times negative 16 times 136, and then take the square root of that. That gives you t equals negative 30 plus or minus 98 divided by negative 32. Okay, so if we do negative 30 plus 98 divided by negative 32, that gives us t equals negative 2.125 seconds. And if we do negative 30 minus 98 divided by negative 32, that gives us t equals 4 seconds. Right off the bat, you can immediately get rid of this answer. You cannot have a negative time. That doesn't even make sense, okay? We're not going to have time going backwards. So that means our only answer is going to be 4 seconds. So it will take 4 seconds for the rock to be 89 feet above the water, okay? And that, it should sort of make sense why we had to get rid of this one. I mean, of course we know we can't have a negative time, so we have to get rid of it. But remember, we started at 225 feet above the water, right? So we would have to go down, down, down. We'd have to sort of go backwards in time to get to 89 feet, right? That's what this is kind of telling us, okay? So 4 seconds would be our answer. Let's look at question C now. It says, how long until the rock hits the water? So this is one of those questions where it's not blatantly obvious what we're given, right? Because we don't just see a number. Like with letter B, we saw 89 feet. And we were like, oh, okay, when h of t equals 89, what does t equal? Well, we're not blatantly given a number to sort of work with, so that just means we're just going to require a little bit more thought on our part. We have to interpret this question. How long until the rock hits the water? If the rock has hit the water, you guys, what's the height? 0. The rock is 0 feet above the water, right? It's hitting the water. It's no longer above the water. So it's 0 feet above the water. So we are given an output. We're given h of t equals 0, and we need to find the time. We need to find t, how long, until that happens. So what do? What does t equal when h of t equals 0? So we're just going to plug in 0 for h of t and solve. So 0 equals negative 16t squared plus 30t plus 225. And now we're sort of back to our original a, b, and c. Our a is negative 16. Whoops. My goodness, sorry, I keep trying to grab the eraser. There we go. Our a is negative 16, our b is 30, and of course our c is 225. And we would do the same exact thing that we did for letter B, okay? We're solving for time again, so we need to plug into the quadratic formula. Only now our a is negative 16, our b is 30, and our c is 225. And when we go through and plug it all in, and if you want to, you can pause this video, and you can plug in negative 16 for a, 30 for B, and 225 for C right into the quadratic formula and solve. You should get t equals 4.8 seconds, okay? So it's going to take this rock 4.8 seconds to hit the water. I didn't write out the whole quadratic formula for this, but like I said, if you want, pause the video and plug in your A, B, and C, and you should get 4.8 seconds, all right? How high above the water, let's look at letter D, will the rock be after 3 seconds? This one's pretty cut and dry. Okay, we're given a time, 3 seconds, and we want to find the height. How high? So what is h of t equal when t equals 3? Well, all we're going to do is we're going to take t equals 3 and plug it into our original function everywhere we see a t. So this one's actually going to be really in comparison to the ones with the quadratic formula, the last two, this one's going to be really nice and easy. So we're just going to plug in 3 for t. So h of 3 equals negative 16 times 3 squared plus 30 times 3 plus 225. And if we do that, we get 171 feet. Okay. So the rock will be, let's always interpret your answer. Say it back to yourself in a sentence. The rock will be 171 feet above the water after 3 seconds. That's what that means, okay? And then, of course, you guys knew I was going to ask you. Letter E. What are the real-world domain and range for this function? Okay. So let's think about that for a second. Let's look at letter E. Remember, domain means what are the possible inputs I could have for this function. So how much time basically can go by for this function to make sense. Okay, our input here is time, right? It's t for time. Okay, that's our input. Okay, how much time can go by before this rock hits the water is really what I'm asking you. Well, we already know that, okay? We know it took 4.8 seconds for this rock to hit the water. So that means that our domain, our input time, is going to go from 0 seconds, just right before we throw the rock, to 4.8 seconds, because that 4.8 seconds is going to hit the water, and now our function's basically over for our purposes, right? After 4.8 seconds, it's hit the water, we're done. All right? And remember, our range are the possible outputs, okay? That means we're thinking about what could the height possibly be for this function. Okay, what's the minimum height and the maximum height that we could have for this function? Well, of course, if it hits the water, we're going to be at 0 feet above the water. So the minimum height above the water we could have is 0. And the maximum height we figured out on the last slide was 239 feet. So our range, our outputs that we could possibly have for this function, go from, our rocks either can be as low as 0 feet above the water and as high as 239 feet above the water. Okay? Now, of course, let's just quickly look at this graph. Now, if I had given you the whole picture, the parabola would have gone like this. But I sort of wanted to just give you the piece that we were concerned about, okay? We know that our y-intercept is 225, okay? We started at 225 feet above the water, and then we threw this rock, and it went up for a bit. Not very long, though, and then it started to fall down, and boom, it hit the water right here. So after however many seconds we said that was, like 4.8 or something, 4.8 seconds. We figured that out on the last slide. 4.83 maybe. So you can see that works out really nicely. Okay, our maximum height was 239 feet, right up here. Okay, so this part of the graph is really the only piece that we're concerned about from here to here. That is where our domain and range came in, right? 0, our input went from 0 to 4.83, and our output went from 0 up to 239. So you can clearly see our domain and range there. But I want you to see that, you know, when we're talking about real world context, we're only talking about pieces of these graphs, you guys. So this is the piece of the parabola that we're concerned about, okay? But if I did extend this out, it would, of course, be that lovely parabola shape that we've been talking about, okay? That's the mathematical graph for this. So I hope that this helped a little bit, gave you a nice review, a few some examples for each of the type of functions that we talked about. And please, please, please reach out with any questions that you have for our final. I'm so more than happy to answer them, okay? I wish you all the best of luck, and I know that if you practice and you go through your textbook and you go back into your workbook and you do problems, you go back into your homework and you just do problems, guys, the more you practice, the better you get. So practice, practice, practice what you don't understand, okay? And if you just practice and practice and practice, you will do well, okay? And I am here to help in any way that I can. All right, but congrats on making it to the end. All right, I'll see you guys later. Bye.